So next up, we're going to be doing an example that demonstrates this idea I just mentioned, which is that sometimes you'll have an integral that can't be solved, and when that happens, it's going to be useful to be able to represent um, the initial value problem using definite integrals. So we're going to go ahead and do an example that comes from section 2.2, problem number 5. And in it, we're given this problem. dy dx is equal to e to the minus x squared with y of 0 equals 10. And so we look at this and it's a separable differential equation. So we're going to go ahead and rearrange it. We've got dy is equal to e to the minus x squared dx. And we're going to try to integrate it. Integral dy is equal to the integral of e to the minus x squared dx. You might like get to this point and be like, okay, that's y. And then this thing, I don't really know, and it's plus a constant. You would get stuck because we can't actually evaluate that integral, e to the minus x squared dx. And so this is where it's going to be helpful to, I'm going to write can't evaluate. This integral. This is where it's going to be helpful for us to plug in our initial conditions to the definite integrals so that we can kind of write a solution as best we can. So our left-hand side is an integral with respect to y originally, but we're going to switch it to s. We want it to end at some unknown y, and it starts at our initial y condition 10. On the right-hand side, we've got an integral that we're going to write in terms of general s, just to be kind of precise. And it starts at the initial condition for x, 0, and then it goes up to whatever value x we want to stop at. So the left-hand side, it's pretty easy to evaluate. It's s from 10 to y. So that's just y minus 10. Right-hand side, unfortunately, we can't solve. It's the integral from 0 to x of e to the minus s squared ds. But at least this way, what we could do is we could write y is equal to 10 plus the integral from 0 to x, e to the minus s squared ds. This is kind of like the integral form solution to the initial value problem. So sometimes when you have this type of problem, there's an integral that you can't solve. And so it's okay to represent the solution in terms of the integral as if you could solve it, as long as you have all the relevant information. So we do have our initial condition right there and there. So technically we've solved the problem. What we have right here is just that this is sort of an integral defined function. Which is fine. It's just not what we usually prefer to have, but it's the best we can do in this case. And so that's just an example of that case where it's really important to be able to use this definite integral thing. Any other time you can kind of make your favorite choice. Since we have a bit of time, I'd like to just look at one more example where something kind of weird with our solution can happen. And it's actually going to be that we can't do that final step of solving for y. So this is going to be another initial value problem. We're given cosine of x times e to the 2y minus y dy dx is equal to e to the y sine of 2x with initial condition y of 0 equals 0. So this is a big mess of an equation. There's lots of stuff going on. But our first step is always going to be to move all the y's to one side, all the x's to the other. So we've got e to the 2y minus y right here. We've got a dy that we can keep. And then we've got a sine of 2x over here that we can keep. We're going to move this e to the y over to the left-hand side. We're going to move this cosine x over to the right-hand side. And our dx over to the right-hand side as well. So even though it's a lot more than we've dealt with up to this point, we have separated the equation. And I'm going to go ahead and distribute this fraction right here. So e to the 2y over e to the y is just e to the y. Y over e to the y is just minus y e to the minus y. Like that. And our next step would be to integrate this. And the left-hand side we can do just with integration by parts. So we're going to have e to the y. I think minus y e to the minus y plus e to the minus y. And then on the right-hand side, if we want to integrate that, we're going to have to use a trig identity, which I'm not going to, yeah, we don't have enough time for that. So the solution is going to be minus 2 cosine of x plus a constant. And so looking at this like right now, you could see that we're not going to be able to solve this for y, like y equals a bunch of stuff. That's not going to happen for us. So at least for right now, we're just going to go ahead and plug in our initial conditions and see what we get. So it doesn't look like we can solve y equal to some stuff. So we're going to plug in the initial condition at least. Remember way back when I gave you these steps, oh my goodness, I said using initial conditions and writing y in kind of the final form. Those are interchangeable because depending on the type of problem you have, those are going to occur in different ways. So let's see, we're going to continue this example. So if y of 0 equals 0, then when we have e to the y plus y, e to the minus y plus e to the minus y, oops. Actually, let's just keep that and then use the eraser. So it's minus right there, equal to minus 2 cosine x plus c. If we plug in 0 for all our y's, we're going to have e to the 0 minus 0 times e to the 0 plus e to the 0. And then if we plug in zeros for x, we're going to get minus 2 cosine 0. So that's 1 minus 0 plus 1, so that's 2 over here, is equal to minus 2 times 1 plus a constant. So our constant is 4. So at least we can say right now that e to the y minus y e to the minus y plus e to the minus y minus 2 cosine of x plus 4 is the equation for our problem. So we still can't solve or write y of x equal to some function with no y's on the other side of the equation, which we would call an explicit solution, and it's what we usually like to have. But this equation does work. I'm just going to start that word over. Does work as an implicit solution to the initial value problem. It has y, it has x, it's not a differential equation anymore. Oops, should be an equal sign. And it's incorporated our initial condition. So that's just two different ways that you might have a sort of incomplete solution that still contains all the necessary information.